Second video on momentum, we'll say it's momentum video number 2. So we started to look at an inelastic collision. At least we put the equation down for it with the understanding there are things we have to know initially and there's things we have to know finally in order to solve this. But it is a situation two objects hit each other and then they move apart, and then kinetic energy is lost in forms of other types of energy, sound, heat, work, right? So kinetic energy is lost. Most collisions that we see are inelastic collisions, right? So let's do a 2-dimension one, and then we'll do a 3-dimension one. All right, so let's say we have, pretend that's flat ground. We have a person running. And we'll say we have a football player. We can use my fancy color here. There we go. There we go. And this person has a mass of 52 kilograms, and they are moving to the right with a velocity of 5 meters per second. And why are they running this way? Because there's a person from the other team. They're wearing red. And he's running this way. And let's see. It's tricky finding colors on this. Oh, find some now. Okay, he's carrying his football like this. And we'll give him a helmet. There we go. And this person is a little smaller. We'll give them a mass of 45 kilograms and a velocity this way of 3 meters per second. So they are running straight for each other. And then they collide. And the one thing I know that this person, whoa, goes flying backwards. There it is. And his helmet changes a little bit. This one goes flying backwards with a velocity of 2 meters per second. So what happens to the second person, or what happens to the person on the right, not really the second person, but what happens to this person after the collision? Well, if they bounce off each other, now if they move as one and it's a tackle, they're only going to go in one direction, right? Right, because they're going to be moving as one. So whichever one has the more momentum is the, really kind of determines what direction they go. But these guys are bouncing off each other, right? They hit and they bounce off each other. So this person's going to go flying back. And how much? Well, again, the momentum initial, the total momentum initial is going to equal the total momentum final. So even though we're looking at different situations, the process is staying the same. We find the initial momentum, add it up, get a total. We find the final momentums, add them up, they get a total. Those two totals have to be the same. So it's going to be m of the first guy times his velocity plus m of the second guy times his velocity, and we can get that because it's going to be 52 kilograms times 5 meters per second plus 45 kilograms times a negative 3 meters per second because they're going to the left. So I'm going to do this all in one step, but there's going to be a positive momentum to the right. There's going to be a negative momentum to the left. And then we'll go from there. 52 times 5. And then it's going to be plus 45 times a negative 3. I get a total momentum of positive 125 kilogram meter per second. So that's their total momentum. Well, after the collision, that's got to be the same thing. So that's the total momentum. Again, it has to add up to 125 kilogram meter per second. I'm going to move it up so I got some room. And what has to equal that? Well, it's got to be this guy's momentum plus this guy's momentum. And I know everything about him. So he is 52 kilograms times a momentum of -2 meters per second. And the other person is 45 kilograms. And I don't know this person's final velocity. But again, because I gave some of the information after the collision, I can now solve everything else. If I didn't give the left guy's velocity, I would never be able to get the right guy's velocity. It'd be two unknowns in the situation. I would know how they're related to each other. I could certainly find a relationship between the two of them, their ratio, if you will, something like that. But I couldn't figure out one without knowing the other. All right, so I'm going to solve for velocity final. So it's going to be a negative 104 kilogram meter per second. So I'm going to have to add it to both sides. So 45 kilograms times its final velocity equals 229 kilogram meter per second. And then I could solve for that, divide both sides by 45. My final velocity works out to be a positive number. The guy's going to go to the right, which makes sense. Someone has to go to the right. And there we go. So there's one example of an inelastic collision. And again, just to do it real quick, I'm going to save writing it all out. But if I wanted to find the kinetic energy of the first guy, it'd be 0.5 times his mass times his speed squared. He has a kinetic energy of 650 joules before the collision. This person on the other side, 0.5 times his mass times 3 squared. He has a total kinetic energy of that. And if I added them up, the total kinetic energy before the collision is 852.5 joules of kinetic energy. After the collision, what do we have? Well, we have 0.5 times 52 times 2 squared. This person has 104. This person has a mass of 45 and a velocity of 5.09 squared. This person has a decent amount of kinetic energy. A lot of work was done on this person. They're the one that's going to feel it more later on. And there's kinetic energy of 686.9 joules. So again, we have lost kinetic energy in the forms of sound, heat, and work. All right, moving on. Let's say we have a billiard ball, and a billiard ball is moving this way, and it has a mass of 0.7 kilograms, and it is moving at 10 meters per second to the right. And there's a second one. And even though billiard balls are all the same size, we're going to say this one's bigger, 1.1 kilograms, and it's moving like this. And it's moving at 13 meters per second, where this angle is 50 degrees. Now, after the collision, again, I have to give some information. I have to, because I can't solve. If I just said, what are they doing after? I don't know enough for that. Again, there's too many variables that I don't know. So I'd have to say something. These two collide, and let's just say, for the sake of argument, that this ball, we're going to call it ball number 2. Ball number 2 is now going horizontal. And I think that's enough information. Yeah, I think it is. So let's say that they collide, and after the collision, ball number 2 is now going horizontal. Then the question is, ball number 1, what's its velocity? So let's take a look at this one and see if we can do it. So we have a total momentum before the collision. There we go. And then we have a total momentum after the collision. Now, there's some things I don't know about the after, but I'm going to kind of do this. And then we'll go from there. So I think I gave enough information for this. If not, I might have to say something more. But let's just see. Let's just see if I gave enough. So the first one is 0.7 times 10. So it is 7 kilogram meter per second. The second ball is 1.1 times 13. I'm going to use my calculator for that one. I should probably be able to do it in my head. But 1.1 times 13. This one has a total momentum of 14.3 kilogram meter per second. And let's deal with this one first. Well, it doesn't have a vertical component because it's just moving horizontal. So all of its momentum is 7 kilogram meter per second. That we know. And the next one is, well, now I have to break it up. So it's 14.3 times the cosine of 50 degrees. 9.19 kilogram meter per second. And 14.3 times the sine of 50 degrees. 10.95 kilogram meter per second. Now, I think I have to give an angle. I do. So after this hits, let's keep going with it for a second. So the total momentum vertical is 10.95 kilogram meter per second. Total momentum horizontal looks like 16.19 kilogram meter per second. Now, if I look at the black billiard ball, it has the vertical component. And I know the total vertical is 10.95. And I know ball 2 is only going horizontal. So this must be 10.95 after the collision because the total momentum has to stay the same. So the total vertical momentum has to stay the same. Let me stick to my colors. So this momentum must be 0 because it's not going vertically anymore. And what else do I know? Well, I know these two momentums have to add up to the total, which is 16.19 kilogram meter per second. So I'm not sure what they are, but I know they have to add up to that after the collision. So let's put one more piece of information in here. I can do a few things, but let's say that after they collide, I see that this ball is now traveling at 60 degrees. So let's say that's the case. It's traveling at 60 degrees after the collision. Well, so what do I know? Well, I know for this ball, this is 60 degrees. This I don't know, but this is 10.95 kilogram meter per second. So the 60 degrees I would have to give you at the beginning of the problem, but I can get the other side. So I know the tangent is opposite over adjacent. So divided by the tangent of 60. This side must be 6.32 kilogram meter per second. So this must be 6.32 kilogram meter per second. And therefore I could find what's the momentum of the other ball. Change my color back. 9.87 kilogram meter per second. So I did have to add one piece of information, which I was kind of thinking I did, but that's okay. And I gave that angle there, and that allowed me to find all of the momentums. And if I divide by the masses, I can get all the velocities. So I could do the same type of thing with this, but again, some things. I had to give you two pieces of information. Even though I didn't have to give you velocities, I gave you both directions. And because I gave you both directions, you're able to find the velocities. But there has to be known information about the final in order to find the initial. All right, our next type of collision and our last type of collision is an elastic collision. Two objects hit and move apart, but this is a situation where no kinetic energy is lost in the system, which means there's no sound, there's no heat, there's no work being done. This is a calculation, I'm sorry, this is a collision that we haven't seen probably with our own eyes. Every collision that we see makes some sound, makes some heat, makes some work, something happens in there where it loses kinetic energy. But this is also the type of collision that is by far the most common collision on our planet, right? By far, if we looked at all the collisions that went on our planet in the last 10 seconds, well, 99.9999999 for quite a ways would be elastic collision. So what am I talking about? I'm talking about collisions between air molecules and things like that, and electrons, and all these things that are so small that we can't see on the atomic level. When atoms or molecules strike each other, they don't make sound, right? There's billions of them happening in the room you're in right now, right? There's more than billions. Really, it's an infinite number. We couldn't possibly even think of counting how many there are, right? But there's no sound created in that. It'd be deafening if there was, right? And there's no heat created, or the room would overheat, right? So they collide, and they collide elastically. And again, that's the most common. Now, I'm not going to do an example because I've done enough examples, but I am going to write it out somewhere. So if I was looking at the equation, well, the mass of the first object times the velocity of the first object has plus the mass of the second object times the velocity of the second object. Well, that has to equal the mass of the first times its new velocity plus the mass of the second times its new velocity. That has to be true. Well, this equation doesn't look drastically different than my equation for an elastic collision, right? And they're both the same in what we see. Two objects hit each other and then move apart. So that part stays the same for both of them. Two objects hit and then move apart. The difference is for this one, kinetic energy is lost. In both of these examples, we could see that kinetic energy was lost. In this example, there's no kinetic energy lost, which means I take the kinetic energy of the first object and I take the kinetic energy of the second object and I add them up, I'll get a total kinetic energy initial. And if no kinetic energy is lost, well, then again, that has to equal, I'll call this mass 1 and I'll call this mass 2, the kinetic energy of the first object plus the kinetic energy of the second object. So in this case, we have to satisfy two equations. We have to satisfy this, which is vectors and momentum, and this is what we've done in all the other examples, but we also have to satisfy this because we didn't lose kinetic energy by definition. So kind of back to what I was saying before, with a sticky collision, if you know all the initial, there's only one final. With an inelastic collision, if we know all the initial, we still have to know something about the collision after the end results of that collision. But for one of these, an elastic collision, because we have two different requirements to meet, we have to meet the conservation of momentum law, and we have to, this isn't a law, but we also have to conserve kinetic energy because that's the definition of an elastic collision. If two objects collide and they collide elastically, there again is only one result in the end because they have to satisfy both situations. So I'm not going to do a problem, but again, atoms, molecules, things on the very small atomic level, these things all collide elastically. But what are some things that aren't necessarily completely elastic collisions, but are close enough to being elastic collisions to satisfy this. Well, Newton's cradle is one example. We have all these hard spheres, and they're all on strings, and we pull one and we let it go, and it hits the other ones, and it goes back and hits the other ones, and goes back and forth like that. That's a great example of an elastic collision. Even though it's not perfect, we hear the sound that it creates. It's pretty close. As a matter of fact, the math for an elastic collision would hold up for this because there's such a small amount of kinetic energy lost every time they collide that we could basically say, you know what, that's negligible. We're not even going to worry about it. All right, so stealing this real quick. This is a good example that I'm talking about. There's no work that's going to be done on these. They don't lose shape or anything like that. There's no really heat that's being generated. There's some, but there's not very much. And there's a little sound, but when they collide elastically, which means something. If we pull two balls back and we let it go, then two balls has to come out the other side. It has to, because that's the only way to satisfy both. If we pull three back and they collide, well, then three have to come out, and so on and so forth. Whatever we do on one side, right, we see the same thing come out the other side, because it's not just satisfying momentum, it's satisfying this conservation of kinetic energy, right? So here's a good example. At no time in this can you pull one and two come back just slower. That would satisfy momentum, but it can't satisfy both equations, right? And at no time can we kind of change this and have a different outcome. There is only one thing. So let's let him do it. So again, he pulls back three. Three have to go the other way, right? Because again, that's the only way to satisfy both situations. Let's try. Let's look at a different one. Something like this, same type of thing, right? Only way that it can work. And if they did three on one side and two on the other, which I imagine they do at some point, oh, here we go, then this is the way it has to happen, because it's got to satisfy both equations. So this is a good example of an elastic collision. Other things that we can consider elastic, bumper cars, lots of times we can consider elastic. I used a rubber ball before for an inelastic, but really kind of depends on what it's hitting. But you know, a rubber ball is actually not a bad example of an elastic collision because it doesn't lose shape. It temporarily loses it, then it goes back to its shape, and there's not a lot of sound or heat created. So if we had a bunch of them hitting each other, that would work. So there are things where, you know, they're not elastic collisions, but they're close enough that the math would hold up. All right, we have one more thing to talk about. Let's get this out of our way. We have one more thing to talk about, which is impulse, and we'll do this on the last video.